After studying this module, you shall be able to know the symmetry properties of a molecule with group theory. Define a matrix, special types of matrix, know how to add the matrices, how to subtract the matrices, how to multiply the matrices. Know the special properties of the binary operation of matrices, and also able to find the direct product of this matrix. Now in this module, the symmetry operations which we have defined earlier now will be linked with the matrices. Group and its characteristics were discussed, and scheme of classification of the molecules into point group explained in detail with the help of the flow chart and various examples. Now question arises how to make use of these symmetry properties of the molecules and group theory in solving complex spectroscopic chemical problems. This can be achieved only when we find a procedure to link the symmetry properties of the molecules and mathematical properties, that is group theory. This can be achieved through matrix representation of a point group. That is, each and every symmetry operation of a point group can be represented by a matrix, where a matrix forms the basis for representation. These matrices behave very similar to symmetry operations. Just as various symmetry operations constitute a point group, similarly, matrices corresponding to each symmetry operation of the point group constitute a group. All properties of symmetry operation thus can be reflected into their matrix representation. Now question arises how to represent the effects of symmetry operation on the molecules in mathematical form. Here matrix representation of symmetry operation comes to our rescue. There are a number of theories in mathematics about matrix representation. These theories can be used for solving chemical problems. Before finding matrix representation for a point group, it is very necessary to know the basic of matrix algebra. Now here I will not go in much detail of the matrix algebra, only some of the basic points which are must will be discussed over here. First, definition of a matrix. It is a rectangular array of elements, symbol or numbers, which are arranged in rows and columns enclosed by square bracket. Different from determinant, here we are using square brackets, just like matrix A is shown into the where A11, A12, A1n, these are the row elements, then A11, A21, AM1 are the column element of this matrix. Horizontal rows are called rows and vertical lines are called column. Dimension or size of a matrix means how many rows and how many columns are there in the matrix. In matrix A, there are m rows and n columns. So the dimension of the matrix A is m into n, and generally represented by this symbol of the matrix within square brackets A m into n. First subscript is for row and second subscript is for column. Now where row 1 elements in this matrix A are A11, A12, A1n, and column 1 elements are A11, A21, AM1. The elements in the rows and columns are also known as the entries of the matrix. In general, each entry of the matrix can be written in Aij, that is the element at the intersection of ith row and jth column. Now let us take some special type of matrices common use. Only very few of these special matrices will be given here. First is vector A. Vector matrix. A vector is a matrix that has only one row or one column. These are of two types. Row vector. If matrix has only one row, it is called row vector, A1, A2 up to An. Column vector. A matrix has only one column, it is called column matrix, just like C1, C2, Cn. Square matrix. If the number of rows m of a matrix is equal to the number of columns, that is m is equal to n, it is called square matrix. Matrix B below is a square matrix. In a square matrix, the element of the diagonal are called diagonal element. Here it is shown in between dotted lines, and these are 1, 5 and 8. Then we come to the diagonal matrix. A square matrix is one in which all entries of the diagonals are 0, only the diagonal entries are non-zero, such as in the matrix C, Aij are j, 0, I is not equal to j. 3 to 5 are the diagonal element. One or more or all the diagonal element entries can be 0. Identity matrix. A diagonal matrix in which all diagonal elements are equal to 1 is called identity matrix. It can be of any size. Aij is equal to 0, I is not equal to j, Aia is equal to 1 for all values of I. Identity can be denoted by, identity matrix can be denoted by the symbol capital E or capital I. Let us come to another type of symmetric and asymmetric, antisymmetric matrices. Square matrices for which Aij is equal to Aj for all values of I and j are called symmetric about the main diagonal, or simply symmetric matrices. And matrices for which Aij is not equal to Aj are called antisymmetric element. Then let us go to the next, transpose of a matrix. The transpose of a matrix G of dimension Mn is denoted by A with this sign. Transpose of a matrix G can be obtained by changing its row into column to give G with this G transpose. That is, rows of G transpose matrix are the column of G matrix, and the rows of G matrix are the column of G transpose matrix. Example below shows that G and its transpose G dash are given like this. G 570104 if of 2 is to 3 dimension, and G transpose 570104 3 is to 10. Now orthogonal matrices. A square matrix is said to be orthogonal if it is when multiplied by its transpose gives identity matrix I or E. Now let us take brief about matrix algebra. To understand the application of matrices, one must understand how these matrices are combined, that is, addition, subtraction, multiplication, and a special way of division. Let us look at these characteristics. Matrix addition. Two matrices A and B can be added only if they are of the same size, dimension. Addition is shown in the here A and B and gives us C. Corresponding elements of A are added to the corresponding elements of B. That is 5 plus 6, 2 plus 7, 3 plus minus 2. Like these are added and we get the corresponding elements, and that is given over here 11, 9, 1 and like this. That is, it is a simple addition of corresponding elements. Metric subtraction. Two matrices A and B can be subtracted only if they are of the same size, and subtraction is given by A matrix minus B matrix is equal to D matrix. Here A matrix minus B matrix is equal to C matrix, which is given over here. A minus B is equal to minus C. Here corresponding entries are subtracted. 5 minus 6 is equal to minus 1. 2 minus 7 is equal to minus 5. 3 minus 2 is equal to 5. Like this, all these entries can be obtained in this case. Now let us take matrix multiplication. Two matrices A and B can be multiplied only if the number of columns of A is equal to the number of rows of B. That is, these should be conformable. A of dimension m into p, B of dimension p into n can be multiplied to give the matrix C of dimension n into m. So these should be conformable. Without that we cannot. It is shown we are having A of 2:3 dimension and B of 3:2 dimension, and these are combined as shown. Here it is, we pick up the rows of A, that is row number 1, 5, 2 and 3, and take the column of B, and just see we multiply each and every element of the first row with the column of the second, and these are added in this 5 into 3 plus 2 into 5 plus 3 into 9. Like this we get the entries of matrix C, C11, C12, C21, C22. Again I am saying take the row of the first, multiply with the entries of the column of the second, and like this you get this, and we get the actual multiplication matrix C, which is shown over here, 52 minus 56, 76 minus 88. Again, take the row of the first, multiply with the column of the second, get the symmetry elements of the, get the entries of the C. Division of matrices will not be discussed, as it is not very straightforward and it will be not needed in overview. Some more characteristics of binary matrix operation. Cumulative law of additions. If A and B matrices are of dimensions 1 into n, then matrix A plus matrix B is equal to matrix B plus matrix A is true. Associative law of additions. If A, B and C matrices are of m is to n dimension, then matrix A plus matrix B plus matrix C is equal to matrix A plus the sum of matrix B and C is equal to the sum of matrix A plus matrix B, then matrix C. Associative law of multiplication. If matrix A, B and C are of dimension m into n, n into p, p into q, dimension respectively, then A matrix A multiplied by B multiplied by C is equal to matrix A multiplied with the product of matrix B and C is equal to matrix product of A and B multiplied with matrix C is valid provided the order of multiplication is not changed. Distributive law. If A and B matrices are of m into n dimension and C and D are of n is to p dimension, then A multiplied by C plus D is equal to AC plus AD. A plus B multiplied by C is equal to AC plus BC are valid, and resulting matrix will be of M is to P dimensions, and the results are, it can be easily checked that this law is true. Now, is AB is equal to BA? If product of AB exists, then number of columns of A must be equal to the number of the rows of the B. If BA exists, then the number of columns of B must be equal to the number of rows of A. Now for AB is equal to BA, the resulting matrices from AB and BA have to be of the same size. This is possible only when A and B are square matrices and are of the same size. Even then, in general, AB is not equal to BA. Now for AB is equal to BA, the resulting matrices from AB and BA have to be of the same size. This is possible only when A and B are square matrices and are of the same size. Even then, in general, AB is not equal to BA. Product of matrices in general is non-commutative in nature. These are shown, and it can be easily verified that AB and BA are not the same. Now, if A not equal to 0, B is not equal to 0, AB may be 0 and BA may not be 0. This can be verified as shown. Vectors and operators will not be discussed in these modules. Now, let us take another important property, direct product of matrices. Direct product or Kronecker product of matrices finds application in quantum chemistry and group theory. If a matrix is of n into n dimension and B is the matrix of m into m dimension, then direct product is defined as nm into nm matrix. That is, A direct product of B is equal to C. Here symbol C, which is shown over here, is a standard notation for direct product. It is not a sign of simple multiplication or addition. It is a way in which the elements of A and B have been combined, taken the direct product. It is shown over here by taking the example of A and B, that is, elements of A are multiplied, each and every element of A are multiplied with each and every element of the B, as shown in this, and we get the matrices of these dimensions. Just it has been explained by taking A 4, 3, 2, 1 and then 3, 1, 2, 1, and we get the entries as 4 into 4 types.
Let us try to understand the direct product between two matrices, let us say A and B, and let it be equal to C. Notice that here this particular symbol is a standard notation for the direct product, and it is not a sign of simple multiplication, which in turn is represented by this symbol. So you can notice the difference between these two symbols, that is, this is the direct product and this is the simple sign of multiplication. Now let us try to understand this with, let us say the matrix A is having these two columns and two rows, and these are the elements. Similarly, let us say that the matrix B is represented by this, and these are the elements, that is B11, B12, B21 and B22. So this is also a 2 by 2 matrix. Now if we have to find out the direct product between A and B, what we will do is, that is, we can say that A with, this is the symbol for direct product, with B will be given by, we can rewrite, that is, it will be this multiplied by this. And let us try to understand how this will be done. So we have these two matrices, multiple being directly, and the direct product of these two will be, we take this matrix and we say that it is being multiplied by this, and this is being represented in terms of this. So what we have to do, we have to take each element of A and multiply it with B. So this can be written as that A11 multiplied by B. Similarly, you can have A12 multiplied by B, A21 multiplied by B, and A22 multiplied by B. So we take this earlier expression and we expand this, that is the direct product of A and B will be, it is A11 with, in place of this matrix B, you will have B11, B12, B21 and B22. That is what we have done is, with A11 we have multiplied the entire matrix B. So this comes in this position. Further, it will be, we take the next term which is A12 into matrix B, and how that will be expanded, it is A12, let us write it this way, and for B matrix, now here this will be multiplied by B11, B12, B21 and B22. Now similarly, when we take this term A21, so it will be A21, let us write it 4 times, and we have to multiply it by this entire matrix B, so we will write B11 here, B12 here, B21 and B22. And now I think it's very obvious how we'll be expanding this term, that is A22 into the matrix B. We write A22 at these places, and it is being multiplied by B11, B12, B21 and B22. So what we get is, you can see this is the matrix which is the direct product of A into B, and notice that both A as well as B were 2 by 2 matrix, and what you have got is the product matrix, and what you have got as the direct product matrix of A and B is, you are having 1, 2, 3, 4 and similarly 4 here, so it is a 4 by 4 matrix. Now let us try to take an example to find out the direct product, and let us take that we are given that A is 4, 3, 2, 1, this is the 2 by 2 matrix, and another matrix given B is 3, 1, 2, 1. So now in this case, the direct product, that is A, and this is the direct product symbol with B, will be given by, what we have to do is, we have to take this first element of A, that is from the first column and first row, and we write it at these 4 places. And what we'll do is, we'll take all these elements of B and write in respective places, that is, it is 4 into 3, 4 into 1, it is coming from this position, then 2 will come here and this one will come here. Now let us take this element which is 3 for the matrix A, so we write 3 here, we write 3 here, here and here. And now this is being multiplied by all these 4 one by one, that is 3 multiplied by 3, 3 multiplied by 1, 3 multiplied by 2 and 3 multiplied by 1. Similarly, we now take this particular element of the matrix A, it is 2, and we write 2 at these 4 places, and what we'll do is we'll multiply by 3, then 1, then 2 and then 1 in these respective places. That is, what we get is 2 multiplied by 3, 2 multiplied by 1, 2 multiplied by 2 and 2 multiplied by 1. Now similarly, taking this element, which is the second row and second column element for matrix A, we will write this here, here, here and here, and we will take these 4 elements of matrix B and multiply them here. That is 1 multiplied by 3, 1 multiplied by 1, 1 multiplied by 2 and 1 multiplied by 1. And this is the 4 by 4 matrix that we have obtained. That is, you can clearly solve it further. So what we get, you can clearly see, is now 4 into 3, you get 12 here, 4 into 1, you get 4 here, 9 here, 3 in place of this, then 8, 4, 6, 3, 6, 2, 3, 1, 4, 2, 2 and 1. So what you can see is this is the direct product between the matrix A and B that we had taken, which were 2 by 2 matrix each, and the product is a 4 by 4 matrix.
Now, after studying this model, we have come now. What is the need for matrix representation? It has been stressed over here. Matrix has been defined and explained. Only some special type of matrices were discussed. Matrix algebra with special reference to addition, subtraction and multiplication has been discussed. Some special characteristics of binary operations of matrices have been mentioned. Without proof, how to find direct product of matrices has been explained by taking suitable example, and this type of properties will be very, very important when we deal in future with this matrix algebra.